So welcome to the IACS Student Seminar. Speaker today is Simon Divilov. Simon is a PhD student working with Marivi Fernandez Serra. He did his undergraduate studies at City College of New York. Marivi has not abandoned Simon. She just can't be here because she's teaching.
Yep.
And this is what he's going to tell us about.
Yeah. Okay. So the title seems a bit esoteric. It's computational experiments meet real experiments and finding the right answer through cross-validation. So before I start talking about, what experiments we're actually talking about, I want to point to you to a problem that we can potentially be facing, and that's the problem of memory storage. And here I have the amount of memory installed by PC versus time. So this is years. And as you see, there's almost an exponential increase with the amount of RAM installed as you go forward in time. And so this is only going to get much worse. So clearly, there's a very large appetite for having a lot of RAM. And I think this is especially true, when you're working with supercomputers, working with, very powerful computers with which you need for simulation. And kind of sticking to the topic of these, while I'm showing some graphs and statistics, it also turns out that for whatever reason, men like to install a lot more RAM on their computers than women. And I'm not sure really what if you can really get anything out of it, but it's kind of interesting that you see that it's kind of in 2008, it's kind of, more or less the same, and it's been diverging ever since. And RAM isn't so easy to acquire as downloading it from the internet. This is a website, downloadmoreram.com, and they let you, and it's a fake website, and they let you select, what RAM you want to download on your computer. But of course, this doesn't really work. RAM is something physical. It just can't be something, downloaded. So this, and therefore, there's been a lot of research going on to develop much better RAM with much higher quality of storage. And so the RAM that I'm going to talk about is specifically non-volatile RAM, and which involves, these things, write memory through resistive switching, and there's a whole slew of methods of how these things write memory. And here, NAND flash is your typical, flash memory, what you have in your, thumb drive, or, maybe, on the memory stick. But there's also these other types of RAM that are candidates to displace flash. Right now, flash is kind of the best. But that's also because there's, a huge industry in flash. And this is Ferroelectric Ram, magnetic RAM, this is phase charge RAM, and this is redox RAM. And it's pretty, this is kind of probably the #1 thing right now. But I want to focus on Ferroelectric Ram because actually, if you see, it's really the first one that was kind of started as a new venue to explore other than flash. But it really hasn't increased, the capacity for storage hasn't really increased that much compared to all these other ways of storing information. And today I'm going to talk about, one of the problems Ferroelectric RAM is facing, in terms of being a real contender with all these other RAM types and, of course, flash. So before, of course, we can discuss Ferroelectric RAM, I have to talk about, Ferro Electricity. And then what I'm going to talk to you about is these layered structures, how we create these devices where you have a layered structure that's ferroelectric, and these have a name, they're called superlattices. And I'm going to talk about the experimental observations and problems they observe in these superlattices. Then kind of where I step in and try to provide some sort of, solutions to the problems that they observe. And finally, we try to match the computational solutions with the experimental observations and see if, things match accordingly, and we really understood what was the problems facing the experimentalists. So to talk about ferroelectricity, I'm going to start with an example. And here's it's a material, and its unit cell is a perovskite, and it has this ABO3 formula, where A is cation sitting on the edges of this cube, or could be also a tetragonal unit cell. B is this center atom, and O is the oxygens, which are on the faces of this cube. And right now what you notice is that because, A is 2 plus, O is 2 minus, each plane here, this is one plane, two planes, and then the third plane, they're all net neutral. So so because everything is net neutral here, there's no way to kind of develop a dipole moment, which, as I'll show you later, is what we talk about when we talk about ferroelectricity and polarization. But what happens if we take this system and we start lowering the temperature? What happens is that this system spontaneously has a transformation, and what happens is that the B cation moves up, and what this means is that now you have a plane of these B cations, which gives you a positive charge, and you have this plane of oxygen anions, which give you a negative charge. So you have this positive negative planes, which create a dipole moment, and a dipole moment, if you divide it by the volume, gives you the polarization, which is something non-zero. And and what's important here is that this occurs spontaneously. So this means that you don't need any external forces to stabilize the state, and that's basically what ferroelectricity is. But there's also this is just one state, and obviously what we want is we want to be able to write information, which is writing zeros and ones on a device. So here, what I'm showing you is something that's called a hysteresis. And so this is the polarization on the Y in the applied field, the applied electric field in the X. And we start in this point over here, and the polarization is 0. And it's 0 because what we have in our device is a random combination of up and down unit cells. And if, on average, if you have, something positive and negative, on average, it's just going to give you 0. So what we start is we start ramping up the electric field, and we flip all of these unit cells to the up state, and that we can say gives you, let's say, a bit of 1. And then as we go back down, we get to the down state, which you can think about as the 0 bit. And you can move between these two states, and you can write a bunch of 1s and 0s. Okay. The one thing that you also notice is that as we move on this curve, we never actually get back to 0 polarization. And that tells you something in terms of the energetics, which is what physicists like to think about. That means the state that has no polarization must be quite unstable relative to these two states. So we can think about this from a diagram, and this is what we call a double low potential. So you have your centrosymmetric state that has no polarization with the higher energy, and you have your two states either up or down at the bottom of this well, which is your stable states. And of course, they both, and the well is symmetric, and that's because, these things are related by mirror symmetry. So there's no real reason, if you flip this one, you get to this one. So there's no real reason why one should have a lower energy than the other. Okay, so now that's kind of a quick, course into ferroelectricity. And now I want to talk about superlattices. And superlattices, like I said, were layered structures. And this is this is a slide from Matt Dauber's group. So the way you create this device is you first have your substrate, which is your base. you start growing an electrode because ultimately you want to do some sort of electrical measurements on this device. And then you grow material A. Maybe it's a ferroelectric, maybe a dielectric, maybe a metal. And then material B. And then you keep alternating how many times you want. And then you finish up with a top electrode to kind of to close the circuit, and so you can actually perform the electronic measurement. And this type of superlattice would have a name. It would be called NM material A material B superlattice, where N and M is the amount of unit cells along this direction of material A, and M is the amount of unit cells along, again, the same direction of material B. And the reason why we want to grow these things is because instead of kind of finding different types of materials for ferroelectrics, we can use one type of material for ferroelectrics and keep changing, which let's say would be material A, and then keep changing material B, whether in the thickness or whatever material, or a different type of material B that would modulate the properties of the polarization, ultimately modulate the properties of your device. So specifically, the type of superlattices we are interested in are lead titanate-based superlattices. So here on the, and I'm going to talk today about two types of these lead titanate superlattices. One is lead titanate strontium ruthenate here on the left. And so lead titanate is your ferroelectric. And you see this is the perovskite unit cell that we talked about before. And strontium ruthenate is a metal. And if you have enough layers, here I only have one layer, so it's just a regular metal. If you add more layers, it could potentially be a ferromagnet. And the other material is lead titanate, strontium titanate. So again, you have your ferroelectric lead titanate, and then you have your strontium titanate, which is a dielectric. And whether you grow this one or this one, it gives you different properties of how your device would behave. Okay, so before I kind of talk about experimental results of these things, I want to draw attention to the hysteresis again. And so hysteresis, here I have on the top, and this is a hysteresis loop like I showed before. And we're measuring this polarization, which is like displacement times charge divided by the volume, or dipole moment divided by volume. And here I have the applied field. Well, it turns out that there's an equally similar measurement you can do to get this more or less the same type of information. It's called a butterfly loop. And what a butterfly loop actually measures, instead of measuring polarization, which is dipole moment per volume, it measures capacitance, which is charge per volume. And while these look, actually figures look quite different, they're related in some nonlinear way. There's a nonlinear mapping where you can go from capacitance to polarization and polarization back to capacitance. And the important thing I want you to get from the fact that these two things are related is the fact that if I shift this hysteresis to the right or the left, there would be a corresponding shift in the butterfly loop from the right, to the right and the left likewise. Okay, so with that, and if you have questions, you can ask, yeah, of course. So with that, if we start now talking about experimental measurements, let's start with an example. And this is, here I have strontium titanate, lead titanate superlattice for a given thickness. Here it happens to be 7 PTO, 7 lead titanate unit cells and 1 unit cell of strontium titanate. And this is your butterfly loop. And one thing you notice right away, maybe about its weird shape, is the fact that it's the center, which is where the two curves cross, is offset from 0. It's offset by about 4 volts. And yeah. Here? That's a good question. It's not something that I know off the top of my head about how much capacitance are in these devices. Because usually I think about this in terms of polarization and not capacitance. But so you see a kind of displacement from the center, and initially this didn't really bother the experimentalists because this is something that's been known for like years and years, this type of displacement. And historically what's been blamed for this displacement is the fact that you have asymmetric electrodes. So here in the bottom you have a strontium ruthenate electrode, and on the top you have a palladium electrode. And so the fact that you have two different electrodes means that, you know, this messes up your electrical measurements and gives you this type of bias offset. Well, it turns out Greg Singh, which is in Dauber's group, he actually grew symmetric electrodes. Here you go, strontium ruthenate and strontium ruthenate top and bottom. And what he noticed is that the bias decreased by about 50%, but actually the bias is still present. And he even tried to make sure that the layer below the electrode was also the same. And again, the bias decreased, but it was still present. And so what this means is that there's something implicit about this bias and must be occurring in the superlattice and not only due to the electrodes. And and this is only for one specific superlattice. So what we want is we want a trend. We want to understand what's happening as we vary different things. So here's the experimental results where I have the bias versus the lead titanate layer thickness. And in red, I have the lead titanate strontium titanate, which is this superlattice here. And what's shown is I increase this lead titanate, the amount of unit cells of lead titanate, the bias keeps increasing with the amount of lead titanate unit cells. And for lead titanate strontium ruthenate, which is here on the left, as I increase the amount of lead titanate unit cells, initially you have an increase the same as lead titanate strontium titanate. But then what happens is that you have the bias becomes, goes negative and decreases with increasing a lead titanate layer thickness. These materials are quite similar, but they have completely different trends with lead titanate layer thickness. And at this point, this is not something that, at this point the experimentalists were stuck and they have to figure out, okay, now they need the input from the theorists because, we can go and do some sort of first principles calculations. But before I start talking about that, I want to talk about, okay, this is a bias offset. So this is a bias offset in either capacitance in the butterfly loop or the hysteresis. What I want to know as a theorist is what happens to the energetics. And to answer that question, we do non-equilibrium dynamics. So what we do is create a toy model hysteresis. So here in the inset, I want you to focus on the inset first. This is energy versus polarization. And I start with, let's say, this purple here, which is your symmetric double well. And what you see is that in the big plot, which is polarization versus applied field, which is your hysteresis, you get a symmetric hysteresis. As now I introduce asymmetry by hand into the double well, where now the negative state becomes more energetically favorable and the positive state becomes less energetically favorable, you see that there's a shift to the right in the hysteresis. So there's a positive bias in the hysteresis. As you successively asymmetrize the double well. And so now we have an understanding, okay, what we want is we want to somehow take this double well, introduce something into the system that's going to make your double well asymmetric. Makes your double well asymmetric. Okay. Now, before I talk about what that is, I want to point out that here I chose by hand the shape of my well. I kind of chose, okay, what type of polarization I want. But in practice, we kind of start with a system and then we want to calculate the polarization because we don't know, a priori, okay, the polarization here should be like, let's say, whatever, 0.5 or negative 0.5. So that brings me to the question of how do we calculate polarization? And this might seem like a trivial question. Why am I focusing on this? And here I I wrote again the equation for polarization, which is just in one dimensions. It's 1 over the length of the unit cell times the sum of the charge times position. You know, kind of what you learn in Physics 101. But turns out things are a bit more nuanced when you have an infinite system, right? You usually think about your material as being huge compared to your unit cell. So usually you think about your system as being infinite. And now what I do is I want to replicate. So what I want to model is I want to model the system, but I only have to model the unit cell because this thing is repeating. So there's two choices. One is the choice here on the left where I have minus charge at A over 4 and then a positive charge at 3/4 times A. And here I have just the reverse. So this is A over 4 and this is 3A over 4. But just, and you see if I make copies of this, I basically get the same type of structure. Yeah. Yeah, exactly. Yeah. There's infinite amount of possibilities. This is just two that I want to try to drive the point about why polarization is not so trivial. So let's go together and let's calculate this quantity, P. So here it's, again, 1 over A, and then you have negative Q times the distance, which is the position, A over 4, plus, because you're doing the sum, positive Q times 3A over 4. So you get Q over 2. Okay, do the same thing for this one. You get Q times A over 4 minus, because you have a negative here, negative charge, times 3A over 4. And you see you get minus Q over 2. So for the same, basically for the same system, you get two different polarization values. And this is kind of the big problem about polarization in infinite systems is that they're not well defined. And this is because, and the way one should think about polarization is not as a static situation, but as a dynamic process. And that's really what's happening in experiments. In experiments, they move from one state to the other state, and then look at the difference. So now what I should be looking at is, you know, I make some sort of perturbation in my system, let's say through an applied electric field, and now my positive charge moves towards the right by a distance of d. So if I now do the same thing, I calculate P, what I end up getting is in both cases, I end up getting a term that's charge QD over A in both cases. What I care about is the difference. What happened? What's the change in the polarization? And as you see, for both cases, the change in the polarization is the same. It's QD over A. And so this means that only differences in polarization are well defined, and that's really how one should think about polarization in infinite systems, as opposed to, let's say, a molecule. Okay. And now one more thing about polarization is that, of course, these things are point charges, and in reality, we have electron clouds, and we don't, things are not just all localized in one location. And these type of things, these localized orbitals, you can think about them, they're called Wannier functions. Usually you want to think about these orbitals as being periodic, but when we think about them as local objects in the unit cell, they're called Wannier functions, and they're related by Fourier transform. But I want you, basically, so this is what I was showing before. Oops. So this is the positive charge, but now you can think about it as the negative charge, but you can think about it as a positive charge with negative electrons surrounding it. So and then you end up with a net negative charge. And what happens is that now your equation moves from this like summing of point charges to summing of the point charges of the nucleus plus summing the electrons, the centers of these Wannier functions or these electronic orbitals. And here maybe things look quite trivial where, okay, I can just see by I where is the center. For real systems, this becomes quite complicated. And here I have Wannier orbitals or functions for silicon and gallium arsenide. And you can see they're very non-trivial. And then, okay, I want to find what are these centers of these orbitals. So things can get hairy once you start moving into real systems. Okay, now kind of finishing this detour, let me talk about the actual superlattice, going back to the superlattice. And I start with a PTO-STO superlattice, lead titanate, strontium titanate. And here for the case I'm going to talk about is a 5-2 lead titanate. So there's 5 unit cells of lead titanate, 2 unit cells of strontium titanate. And now, of course, this is the pristine superlattice, so we know it should have a symmetric double wall. And okay, what do I do to the system? How do I perturb the system to make it so that I introduce an asymmetry? Yeah. Yeah, this keeps repeating itself. Yeah. And the way we do it is we introduce defects. So what we do is we take out this lead cation. So you're left with a negative vacancy, and remove this negative anion, and we're left with a positive vacancy. And so this negative charge, positive charge, gives you a dipole moment. And this is the notation. So this gives you a dipole moment in the lead titanate. Likewise, another unique location where we can have these dipole moments through divacancies is at the interface. And clearly, because dipole moments will couple with the polarization, we expect that these type of perturbations lead to an asymmetric double wall. So now we do this calculation where we calculate, we simulate the system, relax it, calculate the energies, go through the process of calculating the polarization, which is not trivial. And first we end up with the pristine situation, which is the no vacancy case, and as you see, you get a symmetric double wall. Now once we introduce the divacancy either in the lead titanate or the interface, yeah. So, so we're using Wannier functions. So we're doing basically we're doing this. Yeah. Yeah. And so what you notice is that, well, you notice two things. The first thing is that now the wall is not symmetric anymore. And if you remember what I told you, as you make the wall asymmetric, you create a bias in the hysteresis, which is what was seen experimentally.
Sorry,
yeah.
How did you do?
Yeah. Okay. Yeah. Yeah. So what you do is So what you do is you start with a negative state, some negative state, and some positive state. You let the system relax. So you calculate. So and then you have 2 points. You have this point and this point. Yeah. These are 2 grounds. Then what you do is you linearly interpolate the atomic positions and do a one-shot calculation, and that's how you get these points in between. Exactly. Yeah, and then calculate the polarization. Do one step. Don't do any relaxation. You're only relaxing these 2 points. Yeah. And so one thing you notice 2 things. Like I said, the asymmetry in the wall. So one state is has a lower energy than the other state. And the other thing you notice is this shift. As it turns out, I didn't show you this, but this shift actually doesn't have any effect on a measurable hysteresis. The shift that, in fact, you see that this double wall shifted towards the right. Doesn't have a measurable change on the hysteresis. And that's because experimentally, when you calculate hysteresis, let's say they calculate a value of 20 in whatever units. And when they say, okay, that means that the positive state has a value of 10 and the negative state has a value of minus 10, negative 10. When in reality, it might have been 15 and negative 5, which still gives you 20. But this is something experimentalists cannot probe, so this has no effect on something measurable. And while you see this, it turns out to be not of importance. And initially we thought we weren't sure exactly what was this shift, this significance. Mm-hmm. Yeah, so the blue is when you have the divacancy in the lead titanate, and the green is when you have it in the interface here. Yeah, and red is pristine. Okay. So now we basically want to repeat this now for the lead titanate strontium ruthenate situation. And you might say, well, okay, it's just as simple. You have one here, right? But turns out it's more nuanced than that. As it turns out, here I write the layers, the titanium dioxide, lead oxide. Here I have the strontium unit cell. And what it turns out, because if you think about the strontium oxide as a mirror plane, you see that there's no mirror symmetry over this plane. Instead of having a titanium dioxide, as you would have in strontium titanate, lead titanate, you have a ruthenium dioxide. And because you don't have this mirror symmetry, what happens is you get a preferred state as preferred state because of the asymmetry at the interface. You can see this better here, where this is the energy versus polarization. And this is the amount of PTO unit cells, the amount of SRO, strontium ruthenate unit cells. As you see that for different concentrations of lead titanate, you get a slightly different double wall. And the pattern here is that as you increase the lead titanate unit cells, ultimately you should end up with a symmetric double wall potential. But clearly I'm doing 7-1, so you see the wall is pretty asymmetric already. And this is, you're not doing any defects yet. I'm not even talking about defects. Okay, going back to the defects, because of this asymmetry, there's actually a lot of unique positions where you can have your die vacancy. For this talk, I'm really only going to talk about two. One is in the lead titanate over here, this one here. And one here I marked in red. And I marked it in red is because the dipole moment that forms is opposite to the preferred direction of the asymmetry. And it turns out that more or less these things, the other ones end up having the same form as this one over here. The one in the die vacancy in the lead titanate. Okay, so again, we create this double wall potential, calculate the energetics, relax the system, calculate the polarization using Wannier functions. So we start off with the no vacancy case, and like I said before, the wall is already not symmetric, and this is because of the symmetry breaking at the interface. And then once you introduce now, let's say, a die vacancy in the interface, you notice something. Of course, you notice this shifts towards the right, which I said is nothing to worry about because it's not something that can be seen in experiments. But one thing you see is that the negative state became much more stable relative to the positive state. That is, the separation between the negative state in the defect-free situation is much larger than this for the case where you have the die vacancy. And we know this is because we introduced a die vacancy that was opposite in the direction of the asymmetry, so it made the state that was less preferred, more preferred, because the system wants to couple with this defect. And another thing that you notice is for lead titanate, you have this really weird double wall potential. It almost seems like a single wall. And this is kind of where we want cross-validation, because what we see here is this basically tells us, okay, if you have a die vacancy in the lead titanate, you end up with a single wall. Experimentally, we don't actually see that. And so what we know is the cause of this is due to the limitations of our simulations. Because we're constrained in size to make sure the simulation doesn't take forever to run. This has to do with possibly two things. The first thing is that the concentration of die vacancies in our simulation is an order of magnitude higher than it is experimentally because of our constraints, to being able to complete these simulations. Another thing, all these simulations are done at 0 temperature, whereas in principle, these materials are grown at high temperature and they're at room temperature. And that, of course, will change, kind of the phase space. So what we think this is the case, this is correct from the simulation point of view, but this is not something that actually corresponds to reality. Another thing, if you remember, we saw a reversal in the trend, right, with the PTO volume fraction. And what we believe is happening is that, what's supposed to happen at least, we think, is that when you have a low amount of lead titanate unit cells, basically this state is preferred. If you have a high amount of lead titanate unit cells, this state becomes preferred. Now clearly here, this is not the case, it's still this right state that's preferred, but we believe if we did a larger simulation, this state here would go down even further, and then this now would become the more stable state compared to this state. So now to revisit the experimental results, we kind of understand that in lead titanate, strontium titanate, this increase here is due to the fact that you keep having more and more defects in your lead titanate, these die vacancies. And these die vacancies, remember, they cause an asymmetric double wall, and this asymmetric double wall gives you a bias in the hysteresis, or the butterfly loop. In lead titanate, strontium ruthenate, what do we have? What we know is, okay. What we know here is that if you see that the asymmetry is much larger for the lead titanate than this for the, when the die vacancies in the lead titanate is much higher than this for the interface. And as you grow more and more lead titanate, you actually keep the total thickness of the superlattice constant. So what this means is that as you grow thicker and thicker lead titanate superlattices, there's less and less interfaces and more lead titanate. So the amount of die vacancies that you would have in the interfaces decreases, and the amount of die vacancies that you have in the lead titanate increases. So if you can think about it that
Can any property of these die vacancies be measured? Can you count them experimentally?
well, they do have an approximation on the amount of die vacancies that they have, but it's not something that they can see because they can only see like an average of what's happening of the superlattice. So on average, you wash away the die vacancies. So you could never actually see them with like an electron microscope because you just look at the average intensity of the plane, for example, of the average intensity of the atoms.
But does that tell you the total number in the sample? Total concentration?
Yeah, so it's not something that you would be able to like, you would have to, I guess, make some sort of like hand-waving argument. What's the concentration of die vacancies that you have? They know for a fact that they do have it. There's some measurements where they basically they keep running the hysteresis loop like 1,000,000 times, and then they see that the bias decreases, and they know this is because there's a migration of die vacancies. So they know for a fact there's die vacancies, even though these superlattices are grown using state-of-the-art techniques. They know for sure that there are die vacancies, and we indirectly we observe the fact that when they move to the electrode, the bias decreases, so they must be responsible for the bias. So we have indirect measurements that show that die vacancies are responsible for this bias, but we don't have, we cannot see, okay, look, this is a picture of like a die vacancy using like an electron microscope. But there are indirect ways to show that die vacancies are responsible for this, or at least a big chunk of the bias that's being observed. Okay, so I talked about lead titanate, strontium titanate, and then lead titanate, strontium ruthenate. The initial bias is coming from the fact that you have an asymmetric interface, and once you increase the lead titanate layer thickness, the strength of the asymmetry decreases significantly, and then what is causing this bias in this region is the fact that you have die vacancies, and the fact that trend is different is because if you remember that die vacancy at the interface, it has the opposite direction as the direction of the asymmetry. So that's why you have this reversal in the sign of the bias. Okay. And these are kind of my conclusions that I mentioned throughout the talk, that basically this bias cannot be purely explained by electrodes, because once you have symmetric electrodes, you have still this bias being present, while significantly decreased is still present. In lead titanate, strontium titanate, the implicit bias increases with thickness, and in strontium ruthenate, lead titanate, strontium ruthenate, the implicit bias first increases with lead titanate thickness, but then decreases with lead titanate layer thickness past some critical point. And we explain these implicit biases through lead-oxygen divacancies, and we believe they're the most likely candidate based on indirect experimental measurements that we have. And so it turns out that these divacancies do lead to an asymmetric double low potential, which lead to a shift in the hysteresis or capacitance measurement. And in lead titanate, strontium titanate, the largest asymmetry is when you have the divacancy in the lead titanate. And so as we have more and more lead titanate, you have more and more of these large asymmetries coming from the divacancy. And finally, in lead titanate, strontium ruthenate, what happens when you introduce this lead-oxygen divacancy in the interface is it lowers the state opposite to which that was preferred by the symmetry breaking at the interface. So we believe, and we have to test this, we have to confirm this with a larger simulation, with a large enough layer thickness, lead titanate layer thickness, we should see a reversal in which state is preferred. That is, which state is the more stable state. And we believe, once we do this, we have a complete picture to explain the bias that's seen in both lead titanate, strontium titanate, and lead titanate, strontium ruthenate. Okay, thank you. Yeah, go ahead.
So, all your calculations are for an infinite supercell.
Yeah, periodic supercell.
Repetition of your
Mm-hmm.
supercell. Have you ever done a finite size calculation?
I've done with slabs, yes, but not with defects. But nothing too crazy.
Oh,
Yeah.
so what would you say is the relationship between the single slab calculation and the periodic repetition of that same slab? Do those materials have the same properties?
No, they don't, because it turns out that when you do a slab simulation, there's very, very large relaxations at the surface, and specifically when you're doing strontium ruthenate. And these relaxations can change your, basically, now you have finite screening, because strontium ruthenate is a relatively poor metal. It has a relatively low the amount of metallic carriers.
So, but your slab only has
It would only have one.
materials, it doesn't have the electrodes, the substrate?
Oh yeah. So in the slab there are no electrodes. So really the only thing that's providing the screening of the polarization is 1 unit cell of strontium ruthenate, and that's totally not enough. So that's why there's large relaxations at the surface to try to stabilize the polarization. In fact, if you have to go to quite large lead titanate unit cells to actually even get a stable polarization, because usually the system just relaxes to a centrosymmetric state where you have no polarization.
One more question.
Mm-hmm. Yeah.
So, we know a lot about the defects in materials like silicon. And,
Point defects.
yeah,
Uh-huh.
and these divacancies in these layered materials seem to be an important defect. But In silicon, we have ways of probing experimentally the defects. For example, at room temperature, they release carriers, and you can measure the carrier density. And at low temperatures, they bind states, and you can measure the optical properties of the bound states.
I guess, well, also in silicon, it's a much more simpler material. And you can grow very, very like high quality silicon, right? Like very, very pure silicon.
Suppose you do, when you do a calculation for a perfect superlattice, lead titanate, strontium titanate, how big is the gap?
It's about 3V.
So you have a 3-volt gap. Now suppose you put in a divacancy. Do you get states inside the gap?
No.
No bound states?
No. You get states not in, you mean in the center of the gap, or
Anywhere in the gap.
you get states close to, let's say, the edges, but close to the edge.
Close to the edge. Well, that's what you get in silicon. If you dope silicon with gallium, you get a state near the top of the valence.
Yeah. For
See this optically.
because you can just measure the transition. Yeah, I guess also I don't know too much about, I don't know if they did actually any optical measurements. I guess the thing is with optical measurements, you can only probe the surface, isn't it? Right?
I would think that probably the opposite.
The opposite?
In the optical measurements, your sample would be so thin that you wouldn't get as much signal as you would.
I mean, I know because would they have to grow these materials with the electrode? So, yeah.
Any other questions? Okay. Thank you.
Great. Thank you.